Good afternoon, Formby. A pleasure to be here back again one more time. So yes, this is, as you can see, a talk about dark matter, and along the way I'll be answering these two questions: why it's dark and whether or not we think it matters. So it's actually been a long time. It's been nearly 100 years since we've known that the universe has a dark side. It was actually first postulated back in the 1930s, perhaps older than most people would think. And here we see a speaker talking to a group of people saying, after the discovery of antimatter and dark matter, we've just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. So I hope to try and convince you today that dark matter quite definitely does have an influence on the universe in ways that I will describe. So we can start by asking ourselves what the universe is made of. We look out into the universe, we see an awful lot of stuff, and the question is, how can we divide the stuff we know about from the stuff we don't? And it's rather embarrassing to admit that there's more stuff that we don't understand than there is the stuff we do understand. 16% of all the matter in the universe we think we've got a reasonable handle on. That 16%, you'd think, well, what is most of the stuff we understand in terms of matter? Surely it's all the stars in all the galaxies. That must be most of it, surely. Actually, it turns out if we break that 16% down, actually stars are actually only a relatively small part of it. Even though galaxies are made of lots of stars, stars themselves only account for a small fraction of all the matter we understand. Notice that the lion's share on the right-hand side there is actually gas. It's helium and hydrogen. Hydrogen and helium gas between them account for most of what we understand about the universe. Stars are doing their best to take hydrogen and convert it into other elements. Some of those stars have made us, ultimately. But asking what do we understand about the universe, well, it's a lot of gas and it's some stars and it's a few other bits and pieces. That, of course, is ignoring the elephant in the room. And the elephant in the room is, yes, but what's all this 84% that we don't understand? If 16% is all the stars and all the gas and all the dust and everything we can see, what's this 84% of the universe? What's all that about? So I'm going to be saying a little bit about why this dark matter is dark. I'll be looking at the evidence. You could argue that there are at least 4 independent strands of evidence that tell us that dark matter exists. I'm not quite going to have time to cover all 4, so I'm going to cover 3 of them. As always, a handout of the slides is available for anybody that wants to either recap the slides or look at that 4th strand of evidence as well. I'll then be saying, well, if the evidence is that it exists, fine. What is it? And there are only 2 or 3 candidates as to what dark matter can possibly be. And then I'll finish by saying, does it actually matter? In other words, what's the consequences of dark matter actually existing? So firstly, why is it dark? So we can ask the question, why is dark matter dark? And the answer is because it's not light. But that's a little bit flippant to say it's not light. Let's have a little more detailed answer. Dark matter does not behave the way ordinary matter does. Ordinary matter or normal matter, meaning the sort of matter that we are made of. Ordinary matter interacts through what we call the electromagnetic force, which is a posh way of saying atoms can absorb light or emit light, and light, of course, is just an electromagnetic wave. So it comes from the interaction of electric charge in particles in atoms. But although that means we can detect, for instance, the existence of atoms or molecules or anything larger than that through the interaction with light, if atoms absorb light or emit light, then we can detect the existence of atoms through the interaction with light. But dark matter does not interact with light. It doesn't absorb light, it doesn't emit light. And therefore, dark matter does none of those things, has none of those characteristics. Notice one popular misconception: dark matter does not absorb light, so dark matter does not look dark. Things look dark because they absorb light. Dark matter doesn't do that. It would be much more accurate to talk about dark matter as invisible matter, but then that's not quite as catchy as dark matter, so that name has never caught on. But don't think of dark matter as being a large dark cloud of something out there. It doesn't absorb light, and therefore it would not look dark. That's why we cannot see it. Okay, so we know that atoms, that's not necessarily a very accurate picture of an atom, but it's a nice, pretty one. It's got a positively charged nucleus. Every atom has got a positively charged nucleus and is surrounded by a buzzing cloud of electrons, negatively charged electrons. So every atom is a combination of charged particles, positive and negatively charged particles. And that is why atoms interact with light, because light is an electromagnetic wave, and so it interacts with particles which have an electric charge. So that's sort of how we visualize atoms, and we can obviously make our world by thinking that atoms make molecules, and molecules make, well, usually more complex molecules, and eventually molecules make us and other things we see around us. So we understand how the world works in terms of the Earth and the Sun and the solar system and other things based on our understanding of atoms. But what's the evidence that there must be something out there that's presumably not made of atoms? If dark matter doesn't interact in the same way that atoms do, presumably dark matter is not made of atoms. So what is it? Before we think about what it is, let's just make sure we understand that the evidence is out there that something exists beyond our understanding of atoms. So first strand of evidence, I'll number them 1, 2, 3 in the top right-hand corner there. So this is evidence, piece of evidence number 1. When we look at galaxies in clusters, we can ask ourselves, okay, we look out there, we see lots of galaxies throughout the universe. Quite often, these galaxies occur in clusters, not randomly or uniformly spread throughout the entire universe. So what is holding them together? Okay, there's one very bright star in this image, and a lot of these other things are galaxies, these fuzzy blobs. So something must be holding them together, because if something wasn't holding them together, surely they should have just drifted apart by now. We shouldn't ever say that we're at a particular special time when they haven't yet had time to drift apart. We should ask ourselves, there's no particular reason we're observing them now rather than a million years ago or a million years into the future. So presumably, if we see a cluster of galaxies, something must be holding them together. So what is that something? Well, it's not a trick question. The thing holding lots of galaxies together in the sky is gravity. It would appear that gravity is holding them together. Gravity depends on mass, and we think we understand how gravity works. Regardless of whether we take good old-fashioned Isaac Newton to understand gravity or the more modern ideas of Einstein, doesn't make a lot of difference. We are pretty sure we know how gravity works. So gravity can be calculated from the mass of an object. How do we work out the mass of a fuzzy blob in a picture? Well, it's a little bit tricky, but it can be done. We can estimate the mass of a galaxy by looking at how luminous it is. In other words, the more stars it has, the more the mass. The greater the mass, galaxies have large mass if they have lots of stars. So we can estimate the luminosity. We can measure the galaxy's brightness. That's relatively easy to do. Take a picture of it, work out how much light has come into the telescope or the camera. If we understand stars, and generally speaking we do, in other words, we've seen enough stars to be able to tell, we think we know how stars are born, we think we know how stars live, we think we know how stars die. So if we look at a galaxy and there's a particular brightness of the galaxy, we can know, roughly speaking, how many stars there must be, because stars, generally speaking, have a range of brightness. There are some dim stars and some bright stars, but we know, roughly speaking, what the average star looks like. So if we know how bright a galaxy is, we know, roughly speaking, how many stars must be in that galaxy. And if we know roughly the number of stars, then we can estimate the mass of all those stars. Again, because we know that some stars are low mass and some stars are high mass, but we know, statistically speaking, on average, what an average star looks like. So if we know that there are 100 billion stars in this galaxy, we can estimate, well, the average star is this mass, so we can work out the probable mass of that galaxy. I said there roughly, roughly, roughly. It's surprisingly good, mainly because we've got such good statistics. Yes, we don't know exactly what the mass of any particular galaxy is, but because we know there are hundreds of billions of stars, and we've studied many, many millions, if not billions of stars, we have got a pretty good idea of what these averages all work out to be. So simply by looking at how bright a galaxy is, we have a pretty good indication of the mass of the galaxy. And we can do that for all of the galaxies in a particular cluster, and hence we can work out the total mass of that cluster. So now we have an estimate of the mass and hence the gravity that is holding this particular cluster together. But there's a problem. Way back in the 1930s, best part of 100 years ago, it was realized that if you calculate the total mass and hence the gravitational pull of this cluster of galaxies, you find that the gravitational pull is not enough to hold all of those galaxies together. They should have drifted apart millions of years ago, so why do we still see them in the sky? And this is the same regardless of which cluster. It doesn't matter if we choose that cluster over there or that cluster over there. Any of the thousands of clusters of galaxies that have been observed, gravity never appears to be enough by simply adding up all of the mass. Something is wrong. Using luminosity, in other words, using how bright a galaxy appears to be to work out how many stars there are, to work out how much mass there must be, doesn't seem to work. It's an underestimate. And it's not an underestimate by 10% or 20% or 50%. It's wrong by a factor of 3 or a factor of 4 or a factor of 5 or a factor of 6. The gravity we need to hold a cluster together is way more than we can actually account for by counting stars. Even if we've counted them slightly wrong, we can't get that sort of mass. And here's a phrase that will keep cropping up this afternoon. It would appear, it's as if there is some additional mass that's not luminous. In other words, it's mass that we can't see by stars shining. Something is providing the extra gravity that's needed to keep the cluster intact. Something is binding the galaxies together, and it doesn't appear to be all of the things that we can see, all of the stars in all of the galaxies. Something else appears to be out there that is not luminous. What are we going to call it? Don't know. Let's call it dark matter. That sounds really cool. So yes, we've already said we really ought to be calling it invisible matter, but the term dark matter has been around for decades now, and it's stuck. So galaxies, clusters of galaxies, can't exist unless we invoke the existence of something else that we can't see. That's evidence number one. There's a second strand of evidence. We can look at individual stars within galaxies rather than galaxies within clusters of galaxies. We know that all galaxies rotate, and we can work out how fast the stars are moving by using the good old-fashioned Doppler effect. You know, this idea that when a siren is coming towards you, the note changes. As it goes past you and away from you, again, the note drops, the frequency changes. So we can do that with spectroscopy. We don't listen for any stars wailing as they go by. We take a spectrum and we look to see whether or not the spectrum of a star shifts towards the red end or the blue end of the spectrum, indicating that the source of light, the star, is either coming towards us, it could be blue shifted, or moving away from us, red shifted. And so by looking at stars in a galaxy, if you imagine looking sort of obliquely at a galaxy, some of those stars might be coming towards us, some of those stars might be going away from us. And so by looking at the spectrum of those stars, we can see whether the spectrum is shifted towards the blue or shifted towards the red, and that gives us an idea of which way the stars are moving, and the amount of shift is directly related to the speed of the star. So literally by looking at stars and taking their spectra, we can work out how fast these stars are moving in galaxies. Now, we wouldn't want to pick a galaxy which is face-on like this, because you can imagine as this galaxy rotates, all of the stars are moving here in what would be the plane of the screen, so they're not really coming towards us or moving away from us. So that would be the sort of galaxy which would not be suitable for measuring the speed of stars. It would be nice to have one edge on, because quite definitely stars at one side would be moving towards or away from us, and on the other side towards or away from us. But you can see the problem if we're looking at a galaxy absolutely edge on. Notice there's an awful lot of dust down the middle. That tends to be characteristic of spiral galaxies. There's an awful lot of dust which will obscure our view of more distant stars. So although it's ideal in terms of stars moving towards or away from us, it's not ideal because of all this dust. So not face on, not edge on, we want something in between. So we would pick a galaxy that's somewhat more obliquely viewed. And we would then look at as many stars as we could individually see and take the spectra of those stars. They should all be moving sort of in the same direction, so it doesn't matter if we take the spectrum of a group of stars. We'll get an idea of which ones are blue shifted and which ones are red shifted. So this on the right is not supposed to indicate the colors of the stars. It's supposed to be just a schematic indication of stars in this region might be coming towards us and might be blue shifted, and stars in this region might be moving away from us and they might be red shifted. And we can do that for stars at essentially any distance we like from the center of a galaxy. So we can measure the speeds. What would we expect to see? If our understanding of galaxies is correct and all of the mass of the galaxy is simply in the stars that we can see, what would we expect? How should the speed of a star vary as we move from the center of a galaxy towards the edge of a galaxy? Well, if we ask what's happening in the solar system, we know by plotting out the speed of the planets. Here, this graph is velocity on the vertical axis as a function of how far away they are from the sun. And it's clear that planets close to the sun move really fast, like Mercury, and planets further away from the sun, like Jupiter, Saturn, Uranus, Neptune, etc., get slower and slower and slower. That's simply because the pull of gravity from the sun as we go to the outer solar system, the force of gravity falls off as 1/r². So as we go further from the sun, the pull of the sun is weakened, and so the planets are moving much more slowly to stay in orbit. This is what we would expect if the thing keeping us in orbit, the thing keeping the object in orbit, is concentrated there in the middle. Now, physicists wouldn't actually necessarily draw the plot this way. A physicist would draw it on a slightly different set of scales and use log scales because it looks like a straight line. But if we're not physicists, we just say, okay, what we're expecting is the speed will drop off the further away we get from the object that's keeping us in orbit. So we can do that and ask, what would we expect from a galaxy? Well, bear in mind that if we're very close to the center of a galaxy, a lot of the matter is actually behind us. If you think that we're being pulled towards the center of the galaxy, and is that the only thing that's keeping us in orbit? Well, remember, there's an awful lot of mass of the galaxy around us, behind us, to our left, to our right. So the speed we would expect is actually not particularly high when we're in the middle of a galaxy, simply because the mass of a galaxy, unlike the solar system, it's not all concentrated in the center, it's spread over a certain region. So we would expect the speed of a star to increase as we go out from the center of a galaxy. But the important point is, once we get to this sort of area here, once we get to, let's say for the sake of this particular example, 15,000 light years from the center of this galaxy, most of the stars in this galaxy appear to be inside that red ellipse. As far as we can tell, 99% of that galaxy is inside the red ellipse. Maybe there's a few stragglers out there, but most of it is inside. So once we get beyond that point, what would happen at 20 or 25 or 30,000 light years? Surely all of the gravitational pull is coming from inside this red ellipse. So as we go further and further and further away, it should look more and more like the solar system. The source of gravity keeping us in orbit is further and further and further away. Our speed should go down and down and down and down. So we can predict that once we get to the outer edge of the galaxy, this should start coming down, a bit like that dotted line there. So we're not sure exactly what it's going to look like, but we know it should fall. What do we actually see? Well, there aren't that many stars to look at when we get out to 15, 20, 25,000 light years in this particular galaxy. So we can't rely on picking individual stars and saying how fast are they moving. But luckily, we do have lots of atoms out there. And atoms will have exactly the same orbit as a star. Just because an atom is a lot less massive than a star doesn't mean they'll go around the galaxy at different speeds. It only depends on the gravitational pull of that galaxy. So we don't actually use stars, we use individual atoms to go further. And when we extend that yellow line, does it start coming down? No. It either flattens off, or sometimes it even keeps going up and up and up. In other words, the speed of objects as we go further and further and further from the center of the galaxy, those objects are going even faster. How can that be if all of the gravitational pull is from what we can see in the galaxy? Surely the speeds should decrease. It looks like the observational evidence is something is keeping those objects at huge distances from the galaxy. It's keeping those objects moving really fast. It's as if they are being pulled by a significantly higher gravity than we can account for just by looking at where the stars are. Here's this phrase again. It's as if somehow there is some additional mass that is not luminous, because we've accounted for what's in the luminous part of the galaxy, all the stars, but it would appear that once we get beyond that, there's something else providing the extra gravity that's needed to keep stars, or indeed gas, orbiting at very high velocities, even a long way outside what we look at as the visible edge of the galaxy. We can't see any stars beyond the visible edge, but something must be there keeping the stars and keeping the gas moving at really high speed. Again, we don't know what it is. Let's give it the same label. Let's assume that the explanation for this is the same as the explanation for number one. There is some dark matter floating around that we haven't accounted for yet. One way of visualizing that is this little animation, this little cartoon. What do we mean when we talk about the distant stars at the edge of a galaxy moving faster than we expect? Well, you might expect that when we've got a spiral galaxy, this particular video is only a few seconds, so it glitches every once in a while, but you can see that the stars near the center are moving quite fast, and the stars around the edge are moving quite slowly. That's sort of what you would expect in a galaxy. A bit like a solar system. The further you are from the center of the galaxy, you would expect the velocity to start falling away. So that's what we might expect galaxies to look like. But actually what we see when we measure the speed of stars, we find they are indeed moving quite fast close to the center of the galaxy, but they're also moving quite fast at the edge. As you notice here, the edge speed of stars here is much faster than the slow stars we can see here. So the left-hand side is what we would expect, stars moving quite slowly at the outer edge of a galaxy, but what we actually observe is stars moving quite quickly at the outer edge of a galaxy. So what we see is on the right, what we expect is on the left. The only way we can explain what we actually see on the right is to invoke the existence of additional mass, additional matter, which we can't see. Third strand of evidence. Now this is rather different than the previous two, because the previous two have had the same sort of idea. Either galaxies in a cluster or stars in a galaxy. In both cases we need additional mass to hold everything together at the speed they are moving. But evidence number three is a little bit different. We can calculate the mass from its gravitational pull, from its gravitational effect, not on galaxies in a cluster or stars in a galaxy, which is the previous two pieces of evidence we've looked at, but we can look at the gravitational effect on light itself. Yes, I know dark matter does not interact with light. That's what we started with. Dark matter doesn't absorb light or emit light. True. But if dark matter exists, then it has mass, and therefore it has a gravitational effect, and any gravity can, in principle, bend the path of light. So in other words, although the dark matter is not emitting light or absorbing light, it can still influence the way light travels across the universe. In other words, if light is coming, for instance, from a hypothetical distant galaxy in the top right-hand corner, that light doesn't necessarily travel in straight lines to arrive at Earth, because if it travels past a cluster, for instance, a cluster of galaxies, that cluster of galaxies will have mass, and you either think of that mass as simply bending light, or if you wish, you can think of that mass as distorting space. That's the way Einstein chose to view what's going on. Matter distorts space, it warps space and time, and that in turn makes the light travel from the distant galaxy to the Earth. It makes the light travel in curves. So we talk about mass bending light. Even Newton knew this happened. It's not necessarily something specific to Einstein. Newton knew that gravity can make light bend. It's not quite the same amount as Einstein predicted, but it's still there. So if matter can make light bend, all we have to do is look at how much matter bends light. And we can see lots of examples. Okay, only found these really in large numbers when we went to the Hubble Space Telescope, which saw some of these distant galaxies and saw these effects. Prior to the Hubble Space Telescope, we hadn't seen many examples of this, but now we have hundreds or thousands of examples of what can happen when a galaxy, like this orange blob in the foreground, can bend the light from a more distant galaxy. In this case, the distant galaxy is this blue one, which has been distorted out of all recognition from a galaxy that we know and love into what looks like a horseshoe. How can a lens turn a distant galaxy into a horseshoe? Well, you've probably actually seen this, but you don't actually realize it, because the easiest example to give is to say, right, let's look at a distant candle, which is almost a point light source. It's slightly elongated, a bit like a distant galaxy. What if we were to pass the light of that candle through a rather poor quality lens, for instance, the base of a wine glass? Notice that the single point of light now occurs as multiple points of light when the light goes through the base of the wine glass, simply because light going through different parts of the lens gets focused to the observer, or the camera in this particular case. Sometimes we get multiple images. Sometimes those multiple images get stretched out into arcs. Even though the original light source was almost a point of light, the distortion through the lens can get dragged out into arcs. And if you get it lined up just right, those arcs might actually form an entire circle, or indeed a horseshoe like we saw in the previous example. So next time you have a romantic candlelight dinner with your loved one, make sure you look at the candles through the base of your wine glass and observe the lensing effect that we're talking about here. And you may have seen these sorts of examples, whether they've been taken with ground-based telescopes or the Hubble Space Telescope or the James Webb Space Telescope. We now have lots of examples of foreground objects. These sort of slightly orangey objects here are foreground objects, and you notice these rather odd-looking distortions, these lines in the background. These are lines or occasionally arcs. There's one here on the left-hand side. These are all more distant galaxies that have been lensed by the cluster of galaxies in the foreground, producing these distortions. Now, it is rather tricky to work out exactly what's going on. You need a rather complicated computer program to disentangle what's happening. But you can, in effect, say, how big a lens must we have? How much mass do we need in order to bend the light in a way that's consistent with this streak and that streak and this streak and that streak and that streak? It's not an easy calculation to do. It's easier to say, if I know the mass, can I work out how much that mass bends light? It's more difficult to say, if I know how much light is bent, can I work out how much mass must have done that? It's a tricky calculation, but it is a calculation that can be done. And when you work out how much mass do I need to bend space in such a way that I get these galaxies distorted into these shapes, what you find is, when you calculate the mass, we find the mass that is distorting the light is far more than we can account for simply by looking at what galaxies are present. Again, if we add up the mass of the galaxies, what appears to be distorting the distant galaxies is far more, by a factor of 4 or 5 or 6, far more than we can account for purely by adding up the stars. Here we go again. It's as if there is some additional mass that's not luminous. We can't account for it by adding up stars. Something is providing the extra gravity that is needed to bend the light and produce the sort of distorted images that we see. And this is not just one example of one galaxy cluster. This is hundreds or thousands of galaxy clusters all over the sky, all giving us the same information. There is 5 times as much stuff out there than we can account for just by looking at what's visible. So I'm not going to go into the 4th strand, but this appears to be dark matter again, the 3rd piece of evidence, and I'm not going to discuss the 4th piece of evidence, but it's mentioned in the handout if you want to go and have a look. So I hope you're convinced that something is out there. You're not convinced as to what dark matter is, but perhaps you're convinced something is going on that needs an explanation. There's lots of independent evidence that we are not understanding the way the universe works the way we thought it did. Something is out there keeping galaxies together, keeping stars rotating, bending light. What is it? Well, there are a number of candidates. You could argue there are 2 candidates and 1 other possibility. The 2 candidates go by the wonderful name of machos and WIMPs. Yeah, it's not in this order. WIMPs came first. People said maybe there's some particle out there we don't understand. It doesn't interact very strongly, so let's call it a weakly interacting massive particle, WIMP. Some physicists say, I'm not going to research in WIMPs. No, I'm not going to tell people at a cocktail party, what do you work in? I work in WIMPs. No, they said, we're going to have something altogether more macho. What's that going to be then? Okay, macho. What can we reverse engineer out of macho? M-A-C, okay, I'm going to research into massive astrophysical compact halo objects. So this is definitely an example where the acronym came first and then they engineered a description of it. So let me tell you what WIMPs and machos are as the possibilities. Let's do machos first. Massive astrophysical compact halo object. Massive, okay, that's taken as granted. We're trying to find some missing mass in the universe. So whatever these things are, they've got to be massive. Astrophysical means nothing other than that's the A of macho, and you've got to get an A in there somewhere. What about the O? Again, it doesn't mean anything. It's just an object of some kind. What does compact halo object mean? Well, a compact halo object means an object seen in the halo of a galaxy, and the halo of a galaxy is, if you like, a huge sphere surrounding the galaxy. In other words, most galaxies, we can look at where the stars are. We see a lot of stars and a lot of dust. It's assumed that there is a huge halo around every galaxy, and maybe there are objects lurking in that halo. So that's what we mean by a halo object. Compact. Why would these objects necessarily be compact? Well, if they weren't compact, if they were huge stars, we would have seen them already. If they are very massive, big objects, then surely we would have seen them. So compact objects means very small objects like neutron stars or black holes. So small, even if they were glowing, we would hardly be able to see them. So that's a possibility. Are they actually massive objects that we already understand, but they just don't emit an awful lot of light? In other words, are these machos objects such as dead stars, for instance? They are made of normal matter. We don't have to invoke the existence of anything exotic. They're just made of ordinary matter, but they emit no light, or at least they emit very little light. So little light, they appear to be invisible because we haven't got the technology to detect them. They might not emit much light, but that doesn't mean we can't detect their existence. There is still the possibility of saying, well, if it is, for instance, lots of black holes, or maybe neutron stars, maybe white dwarfs, that might sound a bit odd to talk about white dwarfs, because aren't white dwarfs white? Well, yes, they are. White dwarfs, that's what's going to happen to our sun when it comes to the end of its life. It's going to end up as a white dwarf. But a white dwarf, there are no nuclear reactions keeping the star hot, which means it starts its life fairly hot, but it simply cools off. If you wait long enough, a white dwarf will become a black dwarf and will be essentially invisible. So you could argue black holes and neutron stars and white dwarfs that eventually cool down are all objects that are relatively small and relatively dark, hence very difficult to see. So if they are very dim and very difficult to see, if they are out there, how are we going to detect them? Well, this was thought about quite a few years ago. And it was realized that if we think, for instance, that black holes are the answer, if we think that dark matter is simply a whole load of black holes, how can we actually determine that? We can use the same idea of gravitational lensing, i.e. matter distorts space, which bends light. We can think about the same idea, but on a much smaller scale. Not thinking about galaxy clusters bending light from very distant galaxies, but thinking much closer to home. So the idea is as follows here. What if we have a distant star and we're looking at it from Earth? We see that star. It doesn't really matter what we observe it with. We're observing it with some telescope and we're seeing the light from that distant star. If the galaxy is absolutely chock full of black holes, there would have to be a lot of them to account for all the dark matter. If there are lots and lots of black holes floating around out there, we're not necessarily going to see them, but sooner or later, a black hole might drift into our line of sight. If we stare at this star for long enough, that star might not do anything unless a black hole happens to drift into our line of sight. When it happens to be lined up, it's not going to happen very often, but when it does, that black hole is going to focus light in much the same way we saw with a galaxy cluster before. And if a black hole happens to be on our line of sight, we won't see it, but it could focus the light from that distant star, and we would see that distant star temporarily get a little bit brighter. Now, we know about things like, for instance, if a star has planets going around it, the planet can make that star appear temporarily dim by the planet moving in front of the star. But there aren't many ways a star could suddenly get brighter and then go back again. So a star that temporarily brightens, and then as the black hole moves away, the star goes back to its original brightness. This characteristic of stare at a star, and if it suddenly goes bright and then dark and then carries on at its normal brightness, that could be a signature of a massive object, such as a black hole, moving in front of the star, focusing the light. So this experiment was done. You don't pick one star and hope for the best, because this is extremely unlikely. What you look at is 1 million different stars, and you stare at 1 million different stars. You keep imaging stars over and over and over again, and then you watch, you analyze that data to see if any of them show this characteristic spike. So this is an indication of what our Milky Way looks like. We, of course, are inside the Milky Way, but let's just imagine for the moment that we've sort of stepped outside the Milky Way and we're looking at it sideways. There's the center of our galaxy, the most dense part of our galaxy, and it thins out to spiral arms. This is what I'm interested in at the moment. These two satellite galaxies, the Magellanic Clouds, the Large Magellanic and Small Magellanic Clouds visible in the southern hemisphere. If we imagine that we're inside the galaxy and Earth is somewhere around there, again, we're just imagining we've stepped outside for the moment. If we imagine that we are here, what if we were to stare at all the stars in the Large Magellanic Cloud, and there are many, many millions of them? Let's imagine we take image after image after image and watch the intensity of all of those stars over a period of months or years. If there are lots of black holes zooming around in the halo of the galaxy, if the halo contains millions upon millions upon millions of black holes, sooner or later some of those black holes are going to drift in front of the Large Magellanic Cloud, and if they line up with the star, it's going to make that star suddenly brighter. So if we look at how many times does that happen, we can get a feel for how many black holes are there out there drifting around. And the answer is lots. There are indeed lots of black holes floating around our galaxy, but nowhere near enough. If we calculate how many, when we look at these events of stars suddenly getting brighter, we find that we do see these things, but at most they could only account for perhaps a few % of the dark matter we're looking for. So remember, we're looking for dark matter that is more massive than all the stars we can see by a factor of about 5. There are black holes out there, so we are underestimating the mass of the galaxy a little bit, but we're talking about perhaps only a few % of what we're actually looking for. Black holes do not appear to be the answer. Machos do not appear to be the explanation for dark matter. So what's the alternative? WIMPs, weakly interacting massive particles. Massive again, because if they weren't massive, then we couldn't account for all the dark matter we're looking for. Particles, meaning we're not looking for an object, we're not looking for a dead star, we're literally looking for a particle that we didn't know exists. We know molecules are made of atoms, we know atoms are made of protons and neutrons and electrons, etc. But perhaps there's some particle that we've missed up till now, and maybe that is responsible for all the dark matter. So it's a massive particle, and weakly interacting means it doesn't absorb light, it doesn't emit light, it doesn't interact with electromagnetic waves, it doesn't take part in electromagnetic interactions, which is why it's so difficult to find. So that's what we think we mean by a WIMP. It interacts through gravity, it's massive, so it has a gravitational pull, but it doesn't have any electromagnetic interaction. There are other particles that we know exist that are a bit like that. I'm not going to turn this into a particle physics lecture. There are other particles called neutrinos, which are a little bit like that. They have a very small mass, and they don't seem to interact very strongly at all with other forces that we know about, such as electromagnetism. But these WIMPs would have to be substantially more massive than the neutrinos that we know exist. If they exist, they were presumably born in the Big Bang. How else could they exist unless they were born in the Big Bang? And we think that if dark matter particles existed ever since the start of creation, then we think that given that every particle we know of has an antiparticle, electrons have anti-electrons, protons have antiprotons, quarks have antiquarks, all particles seem to have an equivalent, a mirror image, if you like, which looks the same except it's got the opposite electrical charge. Maybe dark matter particles would annihilate with, what do we call them, anti-dark matter, or do we call it dark antimatter? Well, can't quite decide what to call it, but if these things did exist, then any annihilation between dark matter and the antimatter equivalent of that would now be very rare. But where would we expect dark matter to exist? Dark matter does attract itself, and it does attract matter because it's got a gravitational pull. So some people have argued, well, if dark matter is floating around in the solar system, wouldn't it be attracted to the sun because that's a huge gravity well in the middle of the solar system? So maybe there's a lot of dark matter in the sun. So let's go and look for it, because if there is annihilation of dark matter particles in the sun, we might expect to get neutrinos coming out of the sun, and we can measure those on Earth. We've been measuring this particular flux of neutrinos for quite a while. How do we actually determine if this particular particle, a neutrino, comes through Earth? Well, one way of doing that is to build ourselves very large water tanks. And by large, perhaps you can't quite see the scale, but there's 2 people on that gantry there, okay? So this is a very large tank of water. Why would you expect to be able to detect particles flashing through a tank of water? Well, the analogy is to think about what happens when an object moves through the air faster than sound can travel through the air. If you have a supersonic jet, as in this particular case, if it travels faster through the air than sound can travel through the air, you get a shock wave. You get a sonic boom. And there's an analogy for what would happen, what would you expect to happen if a particle travels through water faster than light can travel through water. Now, nothing can travel faster than light in a vacuum, but light gets slowed down in water, so maybe the particle can actually travel faster than light can travel through the water. So there's an analogy. A sonic boom is what happens in air. If you like, a photonic boom is what happens in water. If you ever look at the movies representing what happens in a nuclear reactor, in this case a nuclear reactor surrounded by water, you get this characteristic blue glow. That is not simply Hollywood saying that this looks really cool. You get a blue glow because that blue glow is light that's the equivalent of a sonic boom. It's a photonic boom. It's a flash of blue light every time a particle travels through water faster than light can travel through water. So what we expect to happen in these large experiments is that if a particle comes through, it produces a flash of blue light, and if we have lots of photodetectors, these dots that you can see in the background, if we have lots of detectors picking up that blue flash, we can work out, by looking at which particular detectors picked up the blue flash, we can work out where it came from. And then we can ask ourselves, are these particles that are coming through our detector, are they coming from the sun? Can we explain their existence in the sun? Perhaps, based on dark matter rather than other processes. Just to give you scale, that's what it looks like when you take the water out. And you see an awful lot of detectors in the background there. And if you're having trouble with the scale, this here in the middle is two men in a dinghy. So you can see the scale of this thing. Each of these detectors is rather larger than a basketball, and there are tens of thousands of them lining the wall, lining the curved walls and the top and the bottom to catch every photon of light if a particle comes through and produces this blue flash. That's what the detector looks like. There's lots of them in the previous detector, and they're also used in other detectors around the world where they've decided not to use water per se, but the same idea. At the South Pole, there's an experiment called Ice Cube, where there's a particular laboratory. There's the laboratory sitting on the ice pack of Antarctica, but that's not where the experiment takes place. That's just where the scientists live. The experiment itself takes place underneath the ice cap. Basically, they have drilled down into the ice of Antarctica, and they've produced a string of pearls where, again, these particular detectors, these light detectors, have been put into the ice so that the sensitive area is a cube of ice, 1 kilometer by 1 kilometer by 1 kilometer. Hence, the experiment is called Ice Cube. And because you're finding it difficult to get the scale again, there's the Eiffel Tower to the same scale. The ice pack on Antarctica is more than a kilometer thick. It's a couple of kilometers or so. So this is well down below the top of the ice, so you don't get many stray particles other than the ones you're actually looking for. And that's the actual bedrock of Antarctica itself, which of course is a rocky continent, but it's got kilometers of ice sitting above it. There's no reason why you don't use ice rather than water. The particles really don't give a damn. They are still traveling faster than light can travel. Light traveling through ice is very similar to light traveling through water. The fact that it's solid water rather than liquid water makes very little difference. And it was just decided that this is an interesting way of doing the same thing. You don't have to get a very large tank and fill it with water. Nature has done that for you. You just have to instrument it by putting the detectors in. So these experiments, the large water tank in Japan or this ice cube in the South Pole, these experiments are going on all around the world looking for signs of dark matter particles, WIMPs. In addition to saying that, well, they might be made in the sun because the sun is a gravitational well in our solar system, other people have said, well, that's true, but there's a supermassive black hole at the center of our galaxy. So is it possible that as well as being concentrated in the sun, might there be a whole load of them in the center of the Milky Way galaxy? And maybe annihilation of dark matter particles there might produce gamma rays. Again, we're not going to go through the details of why, but it might be a characteristic of dark matter annihilation producing gamma rays. So we should look to see if there are particles coming from the center of the galaxy that we can't otherwise explain. And indeed, there are, again, a lot of ground-based experiments based on that. So the center of the galaxy, as indicated here, if we imagine stepping out of the galaxy just for the moment, the center of the galaxy here is unfortunately most easily visible from the southern hemisphere. It is visible from the UK, but it's very low down on our horizon. So the idea is you build experiments in the southern hemisphere where the center of the galaxy is a little higher in the sky and easier to access. And experiments that are currently in development, the so-called Cherenkov telescope array, because the blue flash we're talking about is called Cherenkov radiation. Here they're not looking for a blue flash in a tank of water or looking for a blue flash in a cube of ice. They're actually looking for the flash in the sky itself. Because again, these particles that may or may not be coming from the center of the galaxy will be going so fast, they'll actually be going faster than light can travel through air. Now, air doesn't slow down light by much, so light is traveling almost at the speed of light in vacuum when it travels through air, but it's not quite the same as the speed of light in vacuum, and particles can outrace it and produce a blue flash. So telescopes are being built in the, not as indicated in this very early picture that looks like it's in Arizona. No, these telescopes are being built in Chile, and another set to just check what's going on in the northern hemisphere. Another set are being built in the island of La Palma in the Canary Islands. So these telescopes are basically looking up at the sky such that if you do find a really energetic particle coming in faster than light can travel through the air, it'll produce a blue flash, and then these telescopes hopefully will pick up the blue flash. Different telescopes at different positions will pick up different flash in different parts of the sky, and you'll be able to work out where did that particle come from, where did that gamma ray come from, or where did that neutrino come from that's produced this particular flash in the sky, or the flash in the water, or the flash in the ice. So there are a number of big experiments going on to try and find these particles. There are also a lot of smaller experiments going on in labs around the world. Some of the acronyms involved, well, I'm not going to go through them all, but there's lots of labs around Europe and around America and elsewhere where lots of people in bunny suits are trying to build equipment to try and figure out, can we see if a dark matter particle actually visits Earth? If a dark matter particle goes through my instrument, is it possible that it might hit an atom in my instrument? And if I can detect an atom recoiling because it was hit by a dark matter particle, a WIMP, maybe I can actually pick up and detect dark matter. Lots of different experiments going on all around the world. They've been running for years. A number of these experiments have found something, but none of them are definitively, we have found dark matter. A lot of experiments are producing results which are either contradictory or simply a possibility that have not yet been confirmed. So we can't rule it out, but no experiment anywhere on Earth at the moment has found something which we can point at and say that must be evidence for a dark matter particle. So these research projects are all ongoing. Doesn't appear to be machos. If it is WIMPs, we haven't found them yet, and we've been looking for a long time. People have been looking for WIMPs, new particles, for instance, in the Large Hadron Collider. Is there any sign that WIMPs are being made or are interacting with everything else we can see in the Large Hadron Collider experiments? Nothing yet. So we've been looking for dark matter for a long time, and it doesn't appear to be machos, and it doesn't appear to be WIMPs. Have we missed something else? Some people have said, yes, you've missed the obvious thing, and that is it's neither. Dark matter doesn't actually exist. Maybe we've misunderstood how gravity works. We thought we had a good handle on it. Well, we did with Newton, and then Newton got thrown away because Einstein came along and said, no, this is the way to look at gravity. Maybe Einstein's wrong, and we need a third way to look at gravity. So we only seem to need dark matter because we've got gravity wrong. Maybe we're simply doing the sums wrong. Maybe we're doing the calculations in the wrong way that's indicating that we need dark matter, but maybe really we don't. Maybe gravity works differently. Newton said gravity is universal. The gravity pulling an apple to the ground is the same gravity pulling the moon to the Earth. It's the same gravity keeping the Earth going around the sun. It's the same gravity keeping the sun going around the Milky Way. But maybe all those gravities are slightly different. Maybe gravity works differently on different scales. So on the scale of the universe, it works slightly differently to the scale of the galaxy. And it works differently again on the scale of the solar system, or the scale of the Earth, or the scale of the laboratory experiment. This particular idea is called modified Newtonian dynamics, MOND. And it basically says we don't need machos, we don't need WIMPs, we just need to change gravity, which you can do if you wish. You can say Newton was wrong, you can say Einstein's wrong, you can come up with a different way of describing gravity. And as a result, you can get rid of the need for dark matter. Unfortunately, you've solved that problem, but you've invented another 17 problems in the process because it doesn't work for so many other things. So yes, you can sort of engineer or tinker with the theory to get rid of the need for X, but then you need Y and Z and A and B and C, and other things don't work. Nobody has yet found a way of modifying gravity in such a way that you get rid of the need for dark matter and everything else still falls into place. We're not there yet. So does it matter? This stuff appears to be out there. When we run simulations, we think we do definitely need dark matter. We can run simulations that say, how did the universe begin and how do we get from the original universe, a very hot, dense state, very small, how did we end up with an expanding universe in which we are we see full of galaxies. We can imagine that the universe began, given that we now know the universe is expanding and we see an observable universe which is some 100 billion light years or so in diameter, we know that all of those things used to be a lot closer together. If you run the clock back far enough, you can say everything that we currently see in the entire observable universe must have been only a few centimeters apart, if we go back far enough. So the universe started, in a sense, as a sort of cosmic golf ball, and the dimples in the golf ball represent the fact that everything wasn't perfectly uniform in the very early universe. It seemed to be some parts are a little denser, some parts are a little less dense. And we can run simulations that say, well, if we assume that's the case, if we assume we start with relatively uniform matter throughout the universe, but put in very small variations, what does a simulation tell us about the way gravity gets a hold of that and changes things? And this simulation, it's actually down at the bottom if you want to go and check this for yourself. These simulations have been run by lots of people in lots of groups and lots of computers, and they get the same sort of result. If you start with something that's relatively uniform and let gravity do its stuff, what you find is the uniformity changes and the dense parts become even denser and the not so dense parts become even less dense, and you end up getting the density here shown in white. As it gets denser and denser and hotter, you start to form stars and galaxies and clusters of galaxies and superclusters of galaxies. So you started with something that's almost uniform, and you end up with a universe which appears to be a sort of web-like structure. Web with one B, not two B's in this case. And this indeed is what we see. When we look out and look at the universe, we don't see galaxies uniformly spread throughout the universe. We find clusters and superclusters and some areas where there seem to be hardly any galaxies at all. So this web-like structure, this filamentary structure, is indeed the way the universe is put together. And these simulations give us this sort of result, but only if we include dark matter. If we leave dark matter out of the simulations and just say, let's start with a universe full of hydrogen and see what happens, we don't end up with the universe which we see around us today. So it looks like the simulations absolutely need to have dark matter in the mix. On the largest of scales, this is what we think the universe looks like. It's got a foamy, filamentary, web-like structure. Only when we start zooming in to minute detail do we start to see, when we zoom in, we start to see galaxies and clusters of galaxies. On the largest of scales, it seems to be this foamy sort of structure. And we can understand that, and we can understand how many galaxies we might make out of an early universe if we let gravity do its stuff, but only when there's dark matter in the mix. If we leave it out, we cannot understand how we end up with a universe full of galaxies, and we can't understand where we came from. So why is it dark? Because it interacts completely differently. It's different, we think, from ordinary matter. The evidence: galaxies in clusters, stars in galaxies, gravitational lensing, and I haven't talked about it, but the cosmic microwave background also tells us that dark matter exists. We don't know what it is. If it is machos, we haven't found them. If it is simply a whole load of black holes, there must be shed loads of them to account for so much matter, and despite the fact that there must be an awful lot of them, we don't seem to have the evidence for lots of black holes existing. But if it is a WIMP, if it is a new particle we haven't found yet, we've been looking really hard for decades, and we still haven't found what this particle is. So we don't know. Does it matter? Absolutely it matters, because we know that it's an essential ingredient into cosmic evolution. We cannot understand how we end up in a universe that looks the way it does without dark matter. So whether it's machos, or whether it's WIMPs, or whether it's something else we haven't thought of yet, we do need it. Thank you for listening.